A steel rail pressed against a mountain at an angle steep enough that water poured on it would run faster than some trains can climb. That is the physical reality of Mount Pilatus in central Switzerland, where the gradient reaches 48%, nearly 1 meter of vertical rise for every 2 meters of forward travel. No conventional railway could grip a slope like that. Flanged wheels on flat rails simply lose traction and spin. And yet since 1889, a train has been climbing that exact grade, carrying passengers to the summit of a mountain that Swiss engineers originally said could not be reached by rail at all. The question this episode answers is precise. What mechanism made a 48% cog railway not only possible, but continuously operational for more than a century, and what nearly stopped it from being built in the first place? Mount Pilatus rises to 2,132 meters above the town of Alpnachstad on the shore of Lake Lucerne. By the 1870s, Swiss mountain tourism was growing fast. The Rigi Railway had opened in 1871 as Europe's first mountain cog line, and investors saw an opportunity on Pilatus. The problem was that Pilatus was not Rigi. The Rigi line's steepest grade ran around 25%, serious but manageable with the rack and pinion system already in use across Alpine railways. Pilatus nearly doubled that figure. The existing Riggenbach rack system, which used a ladder-style rack rail between the running rails, was rated to handle gradients up to 30% with a reliable safety margin. At 48%, that system would not work. The teeth could disengage under load. A loaded car on a descent could, under the wrong conditions, skip the rack entirely. This was not a theoretical concern. The physics of steep cog railways punishes any gap between the drive pinion and the rack. At shallow grades, gravity pulls the train roughly downward, and the rack teeth stay engaged through the weight of the car pressing toward the mountain. Steepen the grade past a certain point, and the geometry changes. The component of gravity pulling the car away from the rack face increases relative to the component pressing it against the mountain. The rack can unload. Every engineer who looked at the Pilatus project in the 1870s and 1880s understood this, which is why the cantonal government of Nidwalden initially refused to grant a concession. The mountain, they concluded, was simply too steep for a railway. The man who disagreed was Eduard Locher, a Zurich engineer. Locher's insight was not to find a way to force the old rack system to work on a steeper slope. It was to recognize that the old system's geometry was the wrong starting point entirely. He proposed a fundamentally different rack configuration. Instead of a vertical ladder rack between the rails, Locher's design used a horizontal rack with teeth cut into both sides. The drive pinions on the locomotive did not press down onto the rack from above. They gripped the rack from both sides simultaneously, like a horizontal vise, engaging teeth on the left and right faces of the rack at the same time. This meant the pinion-to-rack engagement was not dependent on gravity pressing the train toward the mountain. The grip was mechanical and bilateral. The train could not unload the rack no matter what the grade did to the force geometry. This is the mechanism that made Pilatus possible. The Locher rack system, as it came to be called, solved the 48% problem not by making the train grip harder in the conventional direction, but by changing the direction of grip altogether. The horizontal rack also served a second function. Because the pinions enclosed the rack from both sides, the system functioned as a passive anti-derailment device. The train was physically captured by the rack. It could not lift off, could not shift laterally beyond the tolerance of the pinion engagement, and on descent, the same bilateral grip that drove the car uphill held it back against gravity. Braking on a 48% grade is as critical as traction, and the Locher system addressed both in a single mechanical decision. Construction began in 1886, and the line opened on June 4, 1889. The railway runs 4.6 kilometers from Alpnachstad at the lake to the summit station at Pilatus Kulm. Because the Locher rack geometry required the pinions to stay horizontal relative to the rack, the cars themselves had to be built with a permanent tilt. The floors, seats, and windows are all angled to compensate for the grade, so that passengers sit roughly upright while the car leans dramatically against the slope. This is visible in every photograph of the rolling stock. The car bodies look like parallelograms, leaning uphill, with windows that slant in a way that feels wrong until you understand the geometry underneath. The track gauge is 800 millimeters, narrower than standard, which itself reflects the mountain's constraints. Tight curves and exposed ridge sections demanded the smallest practical footprint. The line includes 4 tunnels and runs along sections of cliff face, where the outer rail has nothing but open air beneath it. Building that infrastructure in the 1880s, on a slope that's steep, without powered equipment, meant moving materials by hand and by animal up terrain that a loaded railway car, even now, requires a specialized rack system to climb. The cost consequence of the Locher system's uniqueness is worth stating plainly. Because no other railway in the world uses this exact rack configuration at this scale, the Pilatus Railway has never been able to source components from a common supply chain. Every rack segment, every drive pinion, every replacement part for the bilateral engagement system has been custom manufactured. That exclusivity has preserved the railway's record. No comparable system has been built steeper, but it has also meant that maintenance and upgrades require engineering work rather than catalogue orders. When the railway electrified in 1937, moving from steam to electric traction, the Locher rack itself did not change. The drive mechanism changed. The bilateral grip that defined the system since 1889 did not. One honest uncertainty is worth naming here. The claim that Pilatus holds the record for the world's steepest cog railway rests on the 48% maximum gradient figure, which is documented and widely cited. Comparisons to other steep railways, including the Mount Washington Cog Railway in New Hampshire, which uses a marsh rack system and is recognized as the world's first mountain climbing cog railway, involve different rack systems, different grades, and different operating conditions. Mount Washington's steepest section approaches 37%, well below Pilatus's maximum. The Pilatus record appears secure on the documented evidence, but the relevant comparison is the rack system's operating limit, not just the headline gradient. What Locher built was not merely a steeper railway. It was a railway that could only exist because it used a rack geometry no one had tried before. Today, the Pilatus Railway carries roughly 400,000 passengers per year in its seasonal operation, running from May through November, depending on conditions. The rolling stock has been updated and the infrastructure maintained, but the Locher rack installed in the 1880s remains the operational foundation of the line. The bilateral horizontal rack that Eduard Locher designed specifically for this mountain has never been adopted anywhere else at comparable scale, not because the principle failed, but because no other railway has needed to operate at this grade. The system exists as a solution to a problem that, outside of Pilatus, no one else has had. That is the actual lesson of the 48% grade. Locher did not push existing technology further along the same curve. He recognized that the constraint Gravity unloading a rack at extreme angles was not a magnitude problem, but a geometry problem, and he changed the geometry. The Riggenbach rack had not failed at 48% yet. It had simply never been asked to try, because every engineer who did the math concluded it could not work. Locher agreed with the math. He just solved a different equation. The next time a railway engineer faces a constraint that every prior design treats as a hard limit, the Pilatus answer is worth remembering. The limit usually lives in an assumption about which direction force has to travel. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.